And okay, so good morning, everybody. Welcome to an overview of standard ranges. My name is Tristan. I'll be your host for the next hour and a half or so. In fact, welcome to an overview of standard ranges special edition. So this is a talk I have given before. I originally gave this talk at CPPCon 2019, and then I was due to do so at ACCU 2020 last year. Obviously, that didn't go ahead for obvious reasons. And so the organisers very kindly asked me if I'd be willing to come back and deliver the talk I was going to do last year, this year, virtually, that you are watching right now. So this is like a special edition HD remaster of the talk I have given, I was due to give last year. And in a sort of weird timeline skew, I have already given the follow-up talk to today's talk. So if by the end of this session, you get to the end and you think this range of stuff is absolutely awesome, I want to know more, then there is a follow-up talk available that you can find online. It's called C++20 Ranges in Practice. So this is the first half, that's the second half. This is the special edition of the first half with all the extra, the DVD extras and all of that. And hopefully with any luck, the ACCU might want me back next year so I can give a special edition of the sequel talk. Right, I hope that all made sense. Anyway, it is traditional to begin with these things with just a little introductory slide. So let's do that. Who am I? Well, my name's Tristan. I'm an independent contractor trainer, usually based in London. I'm a member of WG21, the ISO Standard Committee, and also the BSI C++ panel, the UK national body for standardization, that is. I have a website, tristanbrindle.com, that I very occasionally and infrequently write things on. And if you're interested or curious about the kind of thing I get up to in my spare time, then I have an awful lot of things on my GitHub page, the github.com/tcbrindle. You are more than welcome to go and have a look at that. So that's about me, but let's talk about what we're going to be discussing today. So as the title suggests, an overview of standard ranges. This is a really, intended to be a high-level introductory talk to the new facilities that we now have in C++20. So I'm not going to be delving too deeply into individual features. It's just sort of a broad brush, again, an overview. And intended to give you sort of a flavor of what's, I was going to say what's coming, but it's actually here now. So in particular, I'm hoping that by the end of today's session, I will have been able to answer three main questions for you. Firstly, what is this range of stuff all about? So for a lot of C++ programmers, I think, or a lot of people for whom C++ is maybe not their main focus, but something they do occasionally, they've kind of heard that there's this new ranges thing that we're getting. They're not really sure what it is. Like, is it like D ranges? Is it more like, kind of Swift Rust iterators, something like that? I mean, what is it? So first of all, we're going to start off just what is this range of stuff all about? And in particular, what I suspect people want to know is what's in it for me? For me, as a C++ programmer, what are ranges going to bring? How is my life going to get better with ranges in them? And that's going to form the bulk of today's material. We're going to go over all new features. And hopefully, by the end of that, I will have been able to convince you that ranges are awesome and there's something you're going to want to start adopting in your code as soon as possible. And in order to do that, I'm briefly going to go over at the end the available ranges implementations today, both the standard library ones and a couple of third-party ones. So that's what's on the menu. As I said, I've given this talk before. It was originally an hour-long talk. There's a tiny bit extra in, but one thing I was told about ACCU sessions is they really, really encourage a lot of dialogue between the presenter and the audience. Unfortunately, that's something that's a little more difficult to do with this digital format. But what I'm really hoping is that I will get lots and lots and lots of questions from you today. I'm really hoping that as much as we can with the digital format, we're going to have more of an interactive two-way thing. So please, please, please do, as we're going along, ask questions in the Q&A panel in Zoom, and I will get through as many as we can, because we're going to, all being well, have plenty of time for questions. And well, if we don't, then I guess we all get an early lunch. So it's not all bad. So with that out of the way, let's begin with our first question. What is this ranges stuff all about? So if you really, really, really had to boil it down to the sort of simplest possible description of what the ranges library is fundamentally, if you had to explain it to friends, colleagues, enemies in 6 words, it's STL 2.0. So way back in the past, 1994, I believe it was, Alex Stepanov and Meng Li, they produced this amazing library, which was the HP standard template library, which was, it was a bit before my time doing C++, but from what I understand, this was sort of quite revolutionary. A lot of people quite unsure about it. This new kind of generic programming paradigm did things in very different ways to existing C++ libraries at the time. But that was 1994. 1998, a lot of the STL became part of the first published standard in 1998. And that's what gave us all the algorithms and the algorithm header, vector and list and all the containers and all that good stuff. And then for a long time, nothing really changed. So C++ 11, we got a couple of new algorithms, and the same in 14 and 17, a couple of new overloads of existing algorithms. But by and large, nothing has fundamentally changed between C++ 17 and the original HP STL from 1994. We've had over a quarter of a century of using this fundamentally the same library. And, there are not many sort of, nothing in the world of programming lasts that long, or not many things. So it's a real testament to the solidity of the design, I think. But in that time, the C++ language has changed considerably. So there are lots of new things we can do with C++ that we couldn't do back in the 90s. Lots of new possibilities are offered. So what ranges is fundamentally is a new major release of this algorithms library that we've been using for all this time. So like a new major release, you can expect lots of new features. And the new features, new quality of life improvements are mostly what I'm going to be talking about today. In full disclosure, the fact that it's a new major release, if we were thinking about this in semantic versioning terms, you'd realize that, well, a new major release, this does sort of mean that it's not 100% drop-in compatible with the existing code you might have. So one or two things have changed. I would say it's not 100% backwards compatible. It's probably only 99% backwards compatible. So there are a few changes. The new library is a bit more permissive in some ways. There are one or two ways in which it's a little bit more strict that can trip you up. And in particular, some of the algorithms' return types have changed. This is something to be aware of, and I'll talk a little bit more about that in a moment. So most of the new facilities that we're getting are in this nested namespace std : ranges. So there was the original plan was, I don't like std ranges : ranges. Let's just put that out there right now. This is not my favorite thing. However, it's sort of what we're stuck with now. So the original plan was there was going to be a new top level namespace for this new 2.0 release. And there was some debate about what that should be, and in the end, it was decided that std2 as a namespace, number 2, would be the least bad. And so C++ 17 actually preemptively reserved all namespaces of the form std followed by any string of digits. There's a little bit of C++ trivia for you if you didn't know. So originally the plan was that all new ranges stuff would go in std2, and so instead of saying std : sort, you'd say std2 : sort, for example. After that was done, between the release of 17 and 20, it was sort of decided that a new top-level namespace might not be a great idea. People were sort of worried, okay, so like new code that's not ranges related, does that go in std or std2? And there were lots of concerns, legitimate concerns that I sort of reluctantly agree with. And so all the new facilities are going in this nested namespace std ranges. This is an unfortunate mouthful. It's a lot to type, and it makes the code a little bit ugly, which is a real shame. So what I like to do is I actually just usually use a namespace alias. So I just do like, for example, namespace rng equals std : ranges, and that makes everything look much prettier. So I think I have done. So if you see namespace rng on my slides, it's just short for std : ranges. But the important thing to note is that all of your old code or existing code that's using the algorithms, etc., from namespace standard, it's using things like sort and find and rotate and all these things that are just in std. That code will continue working just as it always has, right? So this is not touching the existing algorithms. Nothing is going to break. All of the new facilities are opt-in. It's a kind of important thing to note. Set people's minds at ease, I hope. And there are several implementations that you can try out today. As I mentioned, if you want to get started, you don't have to necessarily hop on and get the latest bleeding edge compiler. There are other implementations, and yes, we'll talk about those towards the end. So far, I've talked about, I've said the word range, I think, 100, 200 times, who knows, lots and lots of times. And it's probably a useful thing just to take a momentary step back and say, well, what is a range anyway? This library, we're calling it ranges. Well, what do we mean by a range? What is a range? Well, a range is a library, is an object on which one can call begin and end, where begin returns us some object we call an iterator, where this iterator can be dereferenced to give us the value of the element of the range at that position, and the iterator that we can increment, continue incrementing until it's equal to the thing we got from end. And that says, okay, we've reached the end of the range and we can stop iterating. So range is something we can call begin and end. Begin returns us an iterator. Dereference, we can increment. Like, for example, a standard vector. A standard vector is a really good example of a range, a sort of canonical example of a good, well-behaved range. So if this stuff seems familiar, if you're looking at this going, yeah, I know all that, it's because it's pretty much the exact same definition of a range that we have had or notion of a range that we've had since 1994. So ranges don't replace the use of iterators. That's important to note. So this is not if you're familiar with the D language has ranges, but ranges are sort of the lowest level of their stack. They don't have any notion of iterators. Alex Andrescu famously gave a talk saying iterators must go. C++20 ranges are not like that. C++20 ranges don't replace the use of iterators. They build on iterators. So if you are already familiar with what iterators are, what iterators do, how iterators work in C++, then that knowledge is not going anywhere, right? That knowledge, that's fundamentally, that is still the way things work in C++20 with ranges, right? We just have these nice new abstractions on top of iterators. And in particular, the ranges work formalizes many of the notions that we're already familiar with in the STL. So this notion of a range, of input ranges and bidirectional ranges and so on and so forth. We already use these terms sort of informally. But now these things are formally defined and checked, and life is better. But how is life going to be better? What is this new library, this new functionality we're getting? What is it actually going to bring? So the most important question, really, that everybody wants to know why you're watching this overview is what's in it for me? Why are ranges good? Why are you so excited about them, Tristan? What's awesome about ranges? And so for the next, this is going to form the bulk of this talk, and I'm going to go over each or a selected number of new features that I think are great. Again, I will sort of pause at the end of each little mini section to answer any questions. So if you do have any as they come along, please don't hesitate to ask, and upvote any questions that you think are good questions. And also, one thing I forgot to mention is that you'll see a little slide number in the bottom of all of these, or most of the slides, the intertitles. So if there is something on a particular slide that is confusing you, perhaps if I've made any silly mistakes or any typos or anything like that, then do make a note of the slide number, and that way I can go back and we can go back and we can discuss that particular slide. So yes, moving on. The first thing we need to talk about are concepts. Now, concepts, strictly speaking, are not part of the ranges library, but they are a new language feature that we're getting in C++20. Now, again, people who've been sort of following C++ for a while will have been hearing about concepts for a long, long time, because the history of concept is a long and tortured one. So originally, I believe, originally Stefanov was writing about these things he called concepts, back in the 90s. And then for what was then called C++ OX, this very complicated concepts design was put into the draft standard. And again, it's a bit before my time, but this is my understanding. It was sort of taken out pretty much at the last minute, and it kind of pushed back C++ OX so that OX became 11, and C++ 11 was released without these concepts. So the people involved then, after kind of the failure of C++ OX concepts, kind of went back to the drawing board and came back with a new, simpler form of concepts. They called concept. It was originally called Concept Light, and Concept Light became formerly the concepts TS, and then the concepts TS again underwent some more changes and was finally merged into C++20. So we now finally have this thing that the Sentinel has been talking about for a couple of decades, thing that has been wanted in C++ for a long, long time. Now they're available. And in particular, they're available right now today in the latest versions of GCC and MSVC. In fact, GCC has had concepts TS support for a very long time, but now also has support for C++20 syntax for concepts, and as do the latest couple of versions of MSVC. So that's fantastic. The Clang, I believe that the latest release does support the concepts keywords, and most of the functionality is there. But so this is last time I tried it, at least it wasn't a complete implementation yet. There were certain things that weren't supported that you couldn't do. So that may have changed since the last time I tried it. So if I am incorrect in that information, somebody please do correct me. But that is my understanding. So what are concepts? We can kind of get all philosophical about this and mathematical about what concepts kind of are in a sort of represent in an ephemeral sense. Really, somebody a bit more pragmatic. I'm more interested in what concepts actually allow us to do. And what concepts fundamentally allow us to do, their role in the language is that they allow us to control the instantiation of templates by testing syntactic conditions. Control the instantiation of templates by testing syntactic conditions. This is a bit of a mouthful. So again, if you had to really boil it down, if you had to explain it to colleagues, co-workers in just a few words, and this is, again, so people who have a sort of more holistic view of concepts probably won't like this description, but on a practical level, what they actually do, they are something like Svine on steroids. So for those who don't know, Svine is this, I can't even remember what it stands for now. Substitution failure is not an error. There we go. But Svine is this sort of almost abuse of not quite abuse, but sort of a way of bending the template instantiation rules to make certain templates invalid, so they're not considered by overload resolution. And this is kind of something that was discovered, as far as I know, rather than invented. And it's been something that we've been able to do, but it's kind of ugly. It's it's not something you want to have to be an expert on templates to have to learn how to do. I mean, just the name, Svine. No, so concepts are a much more principled, much better way of approaching this problem of controlling which templates and how a templates get instantiated. It's Svine on steroids, Svine in the language. And in particular, a concept is a compile time predicate, which is true if the types that we pass to this concept meet the given requirements. So there is some debate, and I see this written sometimes because, on sort of dark corners of the internet like Reddit, that concepts are pointless. What a load of rubbish. We got standard enable if, we got standard void t. Why do we need concepts? And my feeling whenever I read comments like this is it's a bit like, well, we have standard bind. Why do we need lambdas? Right, we can do all this with some library types. Why do we need support in the language? As well, anybody who's used standard bind and has used lambdas will tell you they will take lambdas any day. Because having support for this in the language, yes, it doesn't, you can do all the same things, but just having that built-in syntax just makes it so much easier, so much more pleasant. So I think concepts are really good. And actually, let's just take a quick look at what a concept actually looks like. So this is not a concepts talk. There are other talks going on at this conference about concepts. And of course, as always, lots and lots of videos available on YouTube. So I'm only going to cover concepts very briefly, but if you are really curious and you want to know more, please go and have a look at those. So here is an example of what is actually a really bad concept. This is not the kind of thing you should write in your own code. Bjarne Strastrup, if you're again, I'm saying if you want to go and do some watching of videos, Bjarne Strastrup has given some talks where he goes into what makes good concepts, and he would say this is a very bad concept. But it's more just to demonstrate the syntax of how these things work. So we've got a concept called string convertible, and we say that this concept requires that given a const reference to a t, so this is like you would have in a function template parameter list, given a const reference to a t, we say t dot, we say that we require that t dot toString compiles, that is, we can call the toString member function on our t, and that the result of that is convertible to. This is a new concept that we're getting in the standard library. The result of that expression of t.toString is convertible to the type standard string. So again, this is not a great concept, and I'm not advocating that you should write things exactly like this in your code, but this is an example of the kind of syntax of the C++20 concept syntax. So we can use our concepts like this. We've got a function template. Again, it's quite a silly thing, but it just fits on a slide. This is convert to string, and we see we write our template type name t, and then we have this requires clause. We say that we require our t to satisfy the string convertible concept. In simple cases, we can actually use a slightly shorter syntax than this. We can put the concept in the template head there. So we can say template string convertible t. And if we want to be really fancy, we can shorten it even further. We can just say convert to string convertible auto constref t. So this is what was the final name for it? The abbreviated syntax, I think. So this function convert to string, it is still a function template. It's exactly equivalent to what we had before. It's just, so just as with generic lambdas, the presence of auto in the parameter list sort of tells you that this is a template. So C++20, the standard library, provides many low-level named concepts like standard same as, standard constructible from. These are sort of the concept equivalent of the things we currently have in the type traits header. So they're things that you can use for constraining templates, but also things that you can use as building blocks for creating your own concepts. So one of the things we can do with concepts is have refinement, essentially. We can build higher level concepts out of lower level ones. And so C++20 provides a lot of these low level concepts, type trait style concepts, which are really useful for building your own high level concepts. And C++20, in fact, does that and has these high level concepts like standard bidirectional iterator and standard random access range. Um, so, sorry. So in particular, we can use these high-level concepts like bidirectional iterator, like random access range, to constrain the algorithms that we have in the standard library. We have constrained algorithms. Now, why is this a good thing? Well, this is best shown perhaps with an example. So I usually like to ask people, what happens when I run this code? If you are fairly experienced with C++, you will know what happens when you try to run this code, right? It's going to explode. This is not going to work. And this is not going to work because standard sort requires random access iteration, and a list iterator is only bidirectional. It's not a random access iterator. And if you are experienced with C++, you of course will know that, and you would never write code like this. But if you are not experienced with C++, it's not really obvious why I can't sort a list, particularly as standard list has a sort member function. So I can call list.sort, but I can't call standard sort of my list. Why? What? Okay. So when you're a bit more experienced, you know there is a good reason for it, but it's not really obvious to a beginner. So they go and they write code like this, and what happens? Well, if we go and do it on everyone's favorite website, you'll see we get, what on earth is all this? So this is, again, I did it on Compiler Explorer just to show you that this is really what happens. This is a really simple program, 10 lines. And as you can see, we're getting 183 lines of error messages from this, what is effectively two meaningful program. Two meaningful lines of code. This is not great. And in fact, this gets even worse if you include more headers, because you can see it's sort of it's saying it can't find a minus operator for the difference type of the iterators. And in fact, if you include more headers, I've only got just the bare minimum algorithm list, but if you include more headers, this gets worse and worse and worse because the compiler lists all the alternatives that it tried. So I tried this with when I had a few more headers in there, and just with kind of vector and string and this output went up to 400 plus lines of error messages for what is effectively a 2-line program, which is just insane. And as C++ programmers, as we get more experience, we actually get really, really good at reading error messages, or sort of scan reading them and picking out the sort of lines, the actual errors, and following these template backtraces. And that's kind of crazy that we need to do that we need to be good at that to be C++ programmers. I think that's kind of crazy. So fortunately, in C++ 20, we have these new constrained versions of the algorithm. So we can say standard ranges sort. And again, we can pass 2 iterators. And so what happens, this is still not going to work, right? Sort still requires random access iteration. So this is still not going to compile, but let's just have a quick look at what happens when we run this, or when we attempt to compile this code with my ranges implementation. So again, this is live on Compiler Explorer, no tricks, nothing up my sleeve. This is the entire error output for this. You can see it's 10 lines, and the first of the 2 messages there, it says candidate template ignored, requirement random access iterator of a list iterator was not satisfied. And the second one, the error message isn't so good, but it's basically telling you that there was the wrong number of arguments, function arguments. Well, it didn't match the range requirements. But I think this, just having this would make such a big difference to the everyday experience of people using C++ and using the standard library. Now, in full disclosure, if you go and you try writing this with current implementations in the standard libraries in GCC or MSVC, you'll see that the error messages actually they're not quite this good yet, right? This is not fake. I haven't made this up. This is with a third-party implementation, my implementation. But hopefully, concepts give us the promise of sort of this style of error messages, much better, more compact, more meaningful, easier to understand error messages when we get things wrong. So I'm really hopeful and confident that eventually we will get there with the standard library implementations as well. They have slightly more difficult than when you have a third-party implementation. But anyway, better error messages, I hope, are going to be one of the really key selling points of this, because people do get things wrong, and when you get things wrong, you don't want hundreds and hundreds of lines of template backtraces. It's madness. The other, I think, major selling point that, again, is kind of a quality of life improvement. It doesn't really bring any new features, but it's just something that makes your everyday life, your everyday experience of using C++ nicer, and that's range-based overloads. So again, this time, this code is going to work, right? We've got a vector, vector's random access. This is all fine. This is going to work. Standard sort, vec.begin, vec.end. This is something, the kind of thing you probably write every day, lots of times a day, if you're anything like me. And we can replace standard sort with standard ranges sort. And again, these calls are now constrained. It's going to check for us that our templates, vector is random access, vector's iterators are random access, and it's going to do all that. But what we can do, we don't have to write this begin and end. This begin and end that we've had to, litter our code with since the beginning of time, we no longer have to do so. We can now, at last, just write standard ranges sort of the vector. We still can provide the first and last iterators if we want to. If we want to, only pass part of a container to an algorithm. But if we just want to operate on the whole range, we can just pass the range object as a whole, just like this. So at last, this is great. There is one slight confession, one slight note of sadness, and that is that only the algorithms in the algorithm header will be rangified in C++20. There are other algorithms in the numeric header, and at the time I wrote these slides, I said we'd have to wait until C++23. I'm actually now that time has progressed a little bit, I'm actually not all that confident we'll get them in C++23 either. But we'll have to wait and see. It's not too late. It may still happen. But yes, only the 100 or so algorithms in the algorithm header have had this rangification treatment. There are a handful of others in the numeric header that haven't had this treatment yet. So just bear with me one moment. Sorry about this. Right. Where were we? Okay, so I've talked about constrained algorithms. I've talked about range-based overloads. These are sort of quality of life improvements. They're not fundamentally anything we couldn't do before. They're just, nicer versions of what we already had. So the next thing I want to talk about is Sentinels. So Sentinels are actually something new, something that we don't have in the existing STL. Because in the existing STL, the end function must return an iterator. Begin and end must return the same type. And so I gave a kind of a hand-wavy description of what is a range right at the beginning of this talk. And I said that the iterator that we get from begin has to compare equal to the thing we got from end, and that tells us when we've reached the end of our range. And the reason this was hand-wavy is because in the ranges world, our end function may return a different type to begin. Our end function may return a sentinel. A sentinel is some type that is equality comparable with. That's one of these low-level concepts that we're getting. So a sentinel is some type that is equality comparable with its corresponding iterator, and which denotes its only job is to denote the end of the range, right? So you can't dereference it, you can't advance it, you can't do anything else with it. The only thing it is required to do is to have operator equals equals and operator not equals with the sentinel type to that range. Okay, so why? What is this for? Why have we done this? Well, using a separate sentinel type, first of all, it actually allows us to simplify the definition of some iterators. If you are one of these people, one of these places that have some custom iterators, using separate sentinels actually makes it easier to write iterators in some cases. So that's kind of nice. Not all that many people write their own iterators, though. The reason I like Sentinels is because in some cases they allow us better code generation. They provide the compiler with more information. They allow us better code gen, that is to say, faster code. So I'll quickly run through a little example. Again, this is for demonstration purposes only, just to show you, try and demonstrate the kind of thing you can do with these separate sentinel types. So we're just going to imagine that we have a function called read file, and it reads in a big string, right? And the thing we know about this read file function, we know for a fact that our big string that we've read in is guaranteed to contain a new line character, a /n, somewhere in it. Because let's say that our read file function, it loads it from disk, and then it just pops a /n on the end of the big string. So we know for a fact that the big string is going to contain a /n. But it might contain more than one. And one of the things we have to do is we have to find the position of the first new line character. We know it contains at least one, might contain more than one. We want to find the first new line character in this string. So how do we do that? Well, we can do so by looking at the first character. Is that a new line? No, it's not. So we look at the second character. Is that a new line? No, it's not. We're trying to find a new line character. And of course, there is an algorithm for that. It is called standard find. So here is how you would do that in C++ 17. We're going to call standard find. We're going to pass the begin and end iterators for our big string. And this is fine. This is going to work. There is no problem with this. This is good code. This is something that would be acceptable, I hope, in most places in C++ 17. This is perfectly good, but it's not optimal. And the reason it's not optimal, it's not necessarily obvious. So to sort of think about that, let's have a quick look at an implementation of standard find. So here's what standard find looks like. Well, a sort of cleaned up, tidied up, nicer version of it. But this is a conforming implementation of standard find. So we just proceed. We say we've got iterators at the start of the range, iterators at the end of the range. While first is not equal to last, while we have not reached the end of the range, we're going to dereference our iterator, check if it's equal to the test value. If it is, we're going to break out of the loop, and we're going to return the iterator that we've got. Otherwise, we're going to increment the iterator and test again. Okay, have I now reached the end of the range? No, I haven't. So I'm going to test dereference and test. The thing is, we have extra information that the compiler doesn't have. We know that our big string always contains a new line character. So we know, we are 100% sure of that, right? So we know that this first condition, this while first not equal to last, that is never, ever going to be satisfied. Because we are always going to break out of the loop before that outer while loop finishes. But in the current STL, we have no way of communicating that to the compiler, to the algorithm. So C++20, again, this is sort of cleaned up and simplified. It changes the definition of standard find or standard ranges find very slightly. So it looks like this. Instead of having two iterators, we now optionally have a different type for first and last. And this is, not much of a change, but it turns out to be quite significant. Because instead of saying standard find just from the beginning to the end of our string, we can change it to say this. We can say ranges find, and we're still going to pass the beginning of our string, but now instead of the end iterator, we're going to pass this special object called unreachable sentinel. Unreachable sentinel is a special type, sentinel type that is compatible with any sort of iterator. And if you ask unreachable sentinel, have I reached the end of the range yet? It is unconditionally always going to say no. Right? It is, as you might imagine, a sentinel you can never reach. Now, this is a dangerous thing to do. This is not something you should do willy-nilly. This is a sharp knife that you should wield with great care. However, it can be a very useful tool sometimes. So to show you what this is doing, here is our rangified, sentinelized version of standard find again. And if we imagine a sort of pseudocode partial type substitution, when we use our unreachable sentinel, the compiler is going to substitute the unreachable sentinel for S. And then it's going to look at this first not equal to last condition. And it's going to, all these functions are inlined. It's going to look at this function definition, and it's going to see that this, first equals last always returns first, always returns false. First not equal to last always returns true. Unconditionally, no matter what. That's literally the definition of the function. So it can inline this, and it can optimize this very, very, very easily to just while true. So we have eliminated a comparison. For each element in the loop, instead of doing two comparisons as we do in the usual case when we are passing the begin and end iterators, by using this unreachable sentinel, we are eliminating one of our comparisons. And again, just to try and prove to you that I'm not inventing anything, I'm not making anything up. Here we have two versions of using this find function. So the first one is just taking the begin and end. The top one's just taking the begin and end of the string. The second one, we're taking the begin iterator, and we're using this unreachable sentinel. And I mean, I have to confess, I can't read assembly code. Perhaps some people out there will tell me exactly what this is doing. I don't know exactly what this is doing, but I can tell you I like the look of the second one a lot better. And it not with this find is just a very simple example. I just wanted to, something that fit in this slide. But I have, using unreachable sentinel in a slightly more complicated case, but by eliminating a comparison in a case where I was absolutely sure we were never going to run off the end of an array, by eliminating a comparison in an inner loop, that one thing allowed the compiler to optimize better around that. And by just changing an end iterator to an unreachable sentinel, I was able to get a 10 times speed up in one particular hot loop. So unreachable sentinel, or sentinels generally, are not something you'll use every day. They are an optimization, but they allow these optimizations, allow range-based code, allow code using the standard algorithms to be as efficient as you would be able to write yourself with a for loop. So again, unreachable sentinel, not something to be used randomly. You know, it's a sharp tool, but it's another tool you can have in your armory to recover performance when it's appropriate. So that was Sentinels. Next thing I want to talk about is projections. You know, a very sort of rushed overview. I'm just going to have a sip of water, if you'll excuse me. So projections, strangely enough, I write a lot of code, all the code I can, using ranges because I like them. But sometimes I have to go back and use older versions of C++. And actually, I find that when I go back and use the original STL, then projections are the feature that I miss the most, which might sound very strange thing to say. Oh, I have a question. What sort of thing could happen if you use the unreachable sentinel when you're not supposed to? So what the unreachable sentinel says is effectively disables checking for whether I have reached the end of the array range. So what you will do is run off the end of an array, and or run off the end of your range, and that's going to be really bad because if you're very lucky, it will crash your program, and if you're very unlucky, it will do worse things than that. So you can only really use unreachable sentinel when you have some other way of terminating your iteration, as we did with find, because in our particular case, we were absolutely 100% sure that it was a safe thing to do. So I hope that answers the question. Please do. Do we have other Sentinels? Not built into the standard libraries in C++20. There are only two. There is something called default Sentinel, which is not particularly interesting. It's just used in a couple of iterator definitions. And there's this unreachable Sentinel, which is, there are, yes, only two in C++20, which is why I used one of those, which is why I used the interesting one in the example. A couple of the views do use separate Sentinel types, but they're sort of private implementation details that you don't have to care about as well. Okay, so projections. So as I say, projections are probably my favorite feature, as strange as it sounds. Hang on, Tristan, what is a projection again? Well, a projection is really simple, right? It's really easy to understand. It's just a unary callable that you pass to most ranges algorithms. Right, okay, yeah, good, thanks. No, a projection is a function object that you pass into an algorithm that modifies the view of the data that the algorithm sees. It's a function object, takes one argument. That argument is the element type of the range. And every time the algorithm dereferences one of your iterators, it's going to pass the result of that dereference through this projection, and then it's going to make decisions based on the projected value that it gets. So to see why this is nice, why this makes things easier, let's have another example. So in this case, we've got a struct employee. Employee has a name and an ID number, and we have a struct payslip we have some pay info. We don't really care what that is. And every payslip has the employee ID attached to it. So we imagine we're writing some accounting software or something like that. And we have a vector of employees and we have a vector of payslips. And what we want to do, it's very, very important. We want to ensure that every month, each employee receives exactly one payslip. Okay, so there's no employees that receive 0. There are no employees that receive 2 payslips, although the employees probably quite like it. But every employee receives exactly one payslip. So there are various ways you could approach this. One way that, given the definitions we have there, that we could do it is by sorting our employees vector according to the ID field, sorting our payslips vector according to the employee ID field, and then comparing these 2 vectors by their respective ID fields to ensure that they contain the same IDs in the same order, right? Again, there are multiple ways you could do this. This is just one way that occurred to me. So what would this sorting approach look like? In C++17, it would look something like this. So we're going to sort our employees vector from beginning to end, and we're going to pass this custom comparator that compares the IDs. And we're doing the same thing with our payslips. We're comparing the employee ID field this time. And then finally, again, we're passing now 2 ranges into standard equal, and we're again passing this custom comparator that compares the employee.id field and the payslip.employee ID field. So, of course, we're getting, I've already mentioned range-based overloads, so we can get rid of all that begin and end stuff. And already this is starting to look a little bit nicer. We can just pass those whole vectors into the algorithms. And we can still pass the custom comparators, just like we always have. But we can improve this further by the use of projections. So to show you what I mean, let's zoom in just on the first of those 3 calls, just on the sort call. And here's what it looks like. And remember what I said at the start of this section. A projection is a unary callable which we can pass to most ranges algorithms, and that projections modify the view of the data that the algorithm sees. Every time the algorithm dereferences an iterator, the result of that dereference is passed through the projection, and then the algorithm makes decisions based on that projected view of the data. So here we have our sort as was. We can, in fact, use pass a projection function. So this, now what we're saying is that we want to sort our employees vector. We want to use the less than comparator. So standard range is less, it's exactly the same as standard less, except uses these new concepts, the concept checked. But it's, so we're using the less than comparator, and we want to project every employee to its ID field. Right, so it's the ID that is being passed to standard less, and each employee is going to have its IDs compared. Now, it's important to note that sort is still sorting the actual employee structs inside the vector. Right, it's not just swapping their ID numbers. That would be no good. Right, so it's only the projection is only being used when the iterator is dereferenced inside the sort call. And most of the ranges algorithms will accept these optional projections. So you see this was this is now an extra parameter. Previously, we were just using 2. Now we've got a 3rd parameter for sort. Most ranges algorithms take these extra optional parameters of projections. So not only sort, but also ranges equal can accept, in this case, 2 projections. 1 projection for the first range, 1 projection for the second range. And for equal, again, we're going to use the equal to function object to compare these things. And you might look at this and go, well, okay, so you've changed the comparator lambdas, the custom lambdas we wrote before for other custom lambdas. This, in fact, we've got more lambdas than we had previously, so this doesn't really seem like a win. But actually, projections have one other trick that I think makes them really, really good. And that is that they are routed through standard invoke. And what standard invoke does, it has a bit of magic in there that allows us to treat pointers to members, pointers to member functions, pointers to member data, as if they were callable. And that's a very long way of saying we can do things like this. So we can, rather than passing those lambdas around, we can now pass this and employee : ID. That is a pointer to member data of the ID field. Now, pointers to members are really, really weird, kind of horrible thing to deal with. If you've ever had to deal with them manually in C++, I wouldn't recommend it. But in this case, all that is handled by the ranges library. All we have to do is sort of use the address of operator on this field. And we can say, okay, I want to sort my employees vector using the ranges less comparator, where each employee is projected to its ID value. And for the last call, we're going to say, okay, I want to call equal. I want to make sure that the employees and the payslips ranges are equal according to this equal to comparator, where each employee is projected to its ID field and where each payslip is projected to its employee ID field. And we can make this even nicer still, because these things, standard ranges less and standard equal to, are the default comparators for sort and equal respectively. We can actually shorten this even further so that it just looks like this. And if I wasn't so worried about lots of space on the right-hand side, you could probably even fit the last one on one line. A question, can we also pass pointer to method, pointer to member function? Yes, you absolutely can. So I was going to show it, but it just takes up a little bit too much room on the slide, unfortunately. But if you have like a getter function, if a payslip was a class that had like get employee ID, you could pass a pointer to the get employee ID function, and that would just work, yes. So here's what we had before. Again, nothing particularly wrong with it. In fact, this is pretty good code as far as C++ 17 goes. But here's the C++ 20 version, and doesn't that look nicer? There it was before. There it is afterwards. I mean, this is, I think this is great. Projections are one of those things where once you get used to them, you start finding uses for them everywhere. Yeah. Sorry, I have a question. Is it as efficient as using lambdas? Usually. There are, okay, so if everything gets inlined, then yes, it is. There are some cases, because pointers to members are not things that get used very often or have not been historically, because the syntax is really ugly and they're just not very nice to deal with. So compilers actually aren't that good at optimizing through pointers to members, not as good as they are at optimizing via ordinary function pointers. So there are, if you sort of layer upon layer these things, it can get a bit too complicated for the compiler to inline all the way through. I think that is probably something that will get better with time as people start to use these sorts of things more often. Compilers will get better at recognizing this pattern and optimizing through it. At the moment, there are some cases in which passing a lambda will generate better code than passing the pointer to member. Again, it's one of those things I wouldn't really worry about unless it turned out to be a problem, you know, in when I was profiling. I think the win of having this lovely syntax is sufficient. And yes, if you go and look at the generated assembly in complicated cases, it can, so occasionally, in full disclosure, not give as optimized code as the lambdas. But and just in case I was misunderstanding, this is, I'm referring to the last slide of passing a pointer to member instead of a lambda. Using a projection instead of a custom comparator, that is exactly the same. That's not going to be any faster or any slower. How is error reporting, for example, if the types of employee : ID and payslip employee ID do not match? Well, what it's going to say is that you've got if you were to, in the last call, if you got those the wrong way around, so if you put the payslips : employee ID argument first, then it's not going to compile, and it's going to tell you that the pointer to member type doesn't match. How good or bad are the error messages? I've got to be honest, I'm not sure. I haven't tried to look at what these error messages are. It's probably one of those things that on the occasions I've done it, I've just looked at it and gone, oh yeah, that's obviously wrong. I haven't really sort of had a good look at the error messages, so I can't really answer that. But that's not anything that's ranges specific. That would happen anytime you mess up your pointer types. What if for some reason I want to actually compare pointers, not dereference? Well, these things are pointers to members. Don't forget, not raw pointers. Are something slightly different. But if you want to do that, well, sure, you just you could just pass a lambda that projects each value to its address. I'm not sure quite why you would want to do that, but you could just, instead of using this like lovely brief syntax here, what you could do is just use a custom lambda that would pass address of whatever the field. Okay. I think that's all of the questions for now. So let's move on to the last little section for this ranges sales pitch, and that is to talk about range adapters. So the standard algorithm, the standard algorithms are great. The standard algorithms are awesome. And as I've just spent the last hour or so talking about, they're going to be getting even better. So use the standard libraries wherever it makes sense to do so. Right? I absolutely encourage that. But unfortunately, there are some situations where the standard library algorithms are not ideal. There are some things where they're just a little bit awkward to use. And the reason for that is because they perform their operations eagerly. So to show you an example of what I mean, let's have a look at this very silly function. That what it does, it takes a vector of ints and it prints the square of each value in this vector, right? This is not, it's an example that fits on a slide, right? However, we are diligent C++ programmers. We listen to the masters, and there is no greater master in C++, in my opinion, than Sean Parent. And Sean Parent says, no raw loops. He doesn't really, certainly doesn't say it in an English accent, but he obviously says this in a much more eloquent way and with lots of justification. And it is most definitely not a blanket rule like this. However, let's sort of take what Sean kind of meant was that you should prefer using named algorithms to like ad hoc for loops with 200 lines that are, that's not good. But we're going to sort of take the spirit of what Sean, and Sean really wasn't talking about like one line for loops that just print every character, right? I don't want to put words in his mouth. But we're going to kind of take the spirit of this and say, okay, well, can we use a standard algorithm instead of our range for loop here? And yes, we can. I think there's more than one way to do this. But one way that we could do it is by using the transform function. So there's standard transform that you're all familiar with. In fact, there are two versions of it. There's unary and binary transform. Here we want to use unary transform. So we're using the rangified version so we can pass the whole vector in. So we want to transform our vector, and we're going to use this lambda function that squares each element, and then we're going to pass the result of that into this output iterator, this O-stream iterator. And the effect of this is that it is going to print out the square of every element. So this is going to do the same thing that we did before. It's just a bit of an uglier way to do it, but there is another way we could do this in C++20. So here we are using ranges transform. That is the equivalent of standard transform. It's just been rangified, right? So it has the concept checks, it has a definite separate sentinel type, it has the facility to pass the whole range, it has all the things that we've been talking about. There is a new version of transform as well on top of this. And that is ranges views transform, or standard views transform. And we can again, this is going to do exactly the same thing. This is going to print the square of every element. But now we're using a transform view instead of a transform algorithm. And what the views transform function does is it takes a range, in this case vec, and a transformation function, and it creates a new range that we're calling view, that when we iterate over this range, performs this transformation on the fly as we dereference each element of the transformed of this view object. So this object here I've called view. It is a range. It has .begin and .end that give you back an iterator and a sentinel. And ranges copy, again, this is like standard copy that we have at the moment. So we're going to copy all of the elements from our view range. We're going to copy all of those into our O-stream iterator. So what's the difference between this version and this version? Well, in a sense, nothing, because they're both at the moment doing a very similar job. Transform is taking an element of vec, computing the square of that, and then passing that to O-stream iterator. But here we're first of all creating this intermediate object we called a view. A view is a range, so we're then passing that to the algorithm, and as it steps through the transformed ranges iterators, as it dereferences them, it's going to in turn dereference the base iterator from vec, and it's going to take the result and it's going to apply this transformation, and it's going to pass that to the ranges copy algorithm. Now, again, just in this simple case, this doesn't really seem like much of a win. Why would we want to do that? And to demonstrate that, we're going to slightly move the goalposts. So instead of just printing squares, what we now want to do is print the squares of all the even numbers in the array in a vector. So now what we're going to do is we're going to say, okay, for every integer in our vector, if the integer is even, that's modulo 2 is 0, then we're going to print it, and we're going to skip the odd elements. So how do we do this with standard library algorithms? only, well, it turns out this is actually not all that easy to do. Transform doesn't like skipping elements all that much. I mean, you could write a custom algorithm to do this if you wanted to, but it's not very easy. I mean, you could do something like this. So first of all, we're going to take our vector and we're going to remove all of the elements, all of the odd elements. So we're only left with the even elements. And then we're going to do the transformation that we did before. But this is, this is not great. Now we've had to take a copy of our vector. You see, I've changed the function argument type from a const reference to just taking by value. We've had to modify our vector, remove if, of course. It's one of those funny things that it doesn't actually remove any elements. It just moves them to the end. Anyway. So we've had to shift about, do 2 passes through our vector, modify it. It's, this isn't great. And this is what I meant by the standard library algorithms are brilliant in the situations where you can apply them. There are some situations where, their eagerness, the fact that they perform all the operations on all the elements in one go, works against them. And this is the kind of situation where that occurs. So let's have a look now at our version using these range adapters. So I factored out the conditions just to make things a little bit tidier. So now we've got a lambda that just tests if an int is even, and we've got a lambda that returns the square of any int we give it. And now, again, we're creating this view object, this view range, and we are transforming something, transforming a range using the square operation. But this time, instead of just transforming vec, we are first using another range adapter called filter. So we're going to take our vec, we're going to filter out all those elements that are odd, and we are going to pass the result of that into our transform adapter. So again, nothing actually happens in this auto view equals blah, blah, blah call. This is just setting up the whole pipeline, right? The magic actually happens when we iterate over this range object, this view object that we've got. Because at that point, what's going to happen is that every time we dereference, every time we increment one of these, the iterators for this, it's going to go down the layers, and it's going to use filter to just skip to the next element where the predicate returns true. And when we dereference, it's going to go through the transform. And so it's going to perform both of these operations, these composed operations on the fly. This is lazy evaluation. This is something functional programmers have been doing for years and years and years. And now we're finally getting it in C++ as well. Standard C++, that is. Okay, so this way I've written it here is kind of ugly. It's sort of inside out because we're doing the filter first and then we're transforming that. And fortunately, we can write this in a much nicer way using this pipe operator. So this is an overload of the bitwise or operator. So what this is saying is we're taking our vec and we're passing it through the filter adapter, and then we're passing the result of that through the transform adapter. So you're supposed to view this as a sort of data pipeline. So the data flows from vec, through filter, through transform. And then we're taking this view object. So again, this is just the setting up this object, this range that will perform these operations. And then we're actually going to iterate over that in the algorithm call. And it's as we're iterating over it, as we're dereferencing the iterators and so forth, that is where the magic happens. So this is sort of the canonical example, by the way. Whenever, it doesn't matter what the language is, whenever anyone is trying to demonstrate this idea of lazy evaluation. So filter and transform is like the example everybody uses. It's possible, however, to build up some really quite complex pipelines with this. So this is from a library that I wrote quite some time ago now. It was using range v3. It's I don't even know if it still compiles, but it's meant to just show you the kind of thing that can be done. So here we're taking a file that is in UTF-8, and we're outputting that same text in big endian UTF-16. So this is a pipeline that does this. So you can see we're reading in the file, we're removing UTF-8 BOM, we're converting to UTF-16 on the fly, we're adding a byte watermark to the start of our range, we're converting it all to big endian, we're writing it out as bytes. This is a data pipeline that you can see exactly what's going on. And as I say, this is just meant to sort of demonstrate what this kind of code looks like. I'm not necessarily saying this is a great idea and that you should do this all the time. It's sort of it's one of the things that I've read about, and I'm probably pretty guilty of myself, is that views range adapters are one of those things where when you first discover them, when they first sort of click, you start wanting to use them for absolutely everything. And that's views range adapters aren't always the best solution to the problem. As I say, if your problem can be solved with one of the eager algorithms, one of the normal ranges algorithms, that is usually a better idea. The code is usually easier to understand. Certainly with current implementations, it's easier for the compiler to optimize. However, views range adapters are really cool. And as I say, these are things that programmers in other languages have been able to do for quite some time. And they let us do really cool things like convert a file from one Unicode encoding to another without ever loading the whole file in memory. That's one thing that's worth noting. So if you're on, I don't know why you'd be doing it on a highly resource constrained system, that sounds silly. But hypothetically, if you were, this never actually loads the whole file into memory. This just does it on the fly. And that is the kind of thing you can do with lazy evaluation. So let me just have a quick scan for any questions. On some platforms, iterators are checked at runtime for validity, and asserts may be raised in certain situations. To your knowledge, are there similar checks for ranges? Yes, basically. The MSVC debug mode has checked iterators. As I say, ranges are based on top of iterators, and almost all C++ 17 iterators are C++ 20 iterators. So those checked iterators will still do the same checks that they did before. Slide 59, can you not pass? Let's go back to slide 59. Can you not pass cout directly without ostream iterator? No, that won't work because transform expects an output iterator. Cout is like an ostream object of some ostream type. It's not an iterator. We have to wrap it in this sort of wrapper object, which provides the ostream, the expected output iterator functions. Couldn't print squares also be realized easily with projections? Yes. So in this particular case, we could use a projection. Well, could we? well, yes, we probably could, but in more complex examples, we couldn't. So this was really just a way of getting into talking about all these range adapters. There are multiple ways to do all of these things. It's quite hard sometimes to boil things down to just simple code that will fit on a slide. In this view, is this view version as efficient as just a plain for loop? Doesn't involve allocating memory for the auto view variable. Is it efficient as a plain for loop? That's a very difficult question, because it's like saying, are the standard library algorithms as efficient as a plain for loop? The answer is usually yes. But it's possible to come up with some examples where, again, a bit like we saw in the Sentinels thing, where you have a bit of extra information that the standard version doesn't have. And you can use that when you're handwriting code. So it is sometimes possible to beat the standard library implementations with handwritten code. So is this view version as efficient as just a plain for loop? It should be when optimization is applied, no less efficient. That's what I'll say, hopefully. Does it involve allocating memory for the auto view variable? There is, it's just going to be, it's going to store a pointer to this. So it's an object that's going to store a pointer to the vector, and that's a stateless lambda, so that's going to be nothing. So it's a couple of bytes in the stack. So nothing to particularly worry about. This absolutely does not do any allocation or anything like that. It's a few bytes for a stack object. And there was a follow-up question that unfortunately I have scrolled away from. And does the range copy do some kind of actual memory copying, or is the compiler somehow optimized all the way? So what this is doing is the OStream iterator is a sort of wrapper around cout. So this effectively is the same as using the double chevron for cout arrow, the result of the thing. So there is no actual sort of mem copying in that sense going on in this example. Anonymous attendee says, is there any reason to use standard sort begin end over standard ranges sort in C++20 and beyond, or any algorithm? No. It's a very short answer. I use the ranges version all the time. Yeah. That's my short answer for that. Yeah. Okay. Why have the range adapters been placed within views rather than adapters namespace? Because they are views. So a view is another kind of concept that is a sort of a sub class of ranges, not a subclass, a subset of ranges are views. Views have particular properties. That's a bit too much detail to go in for today, particularly as we're almost out of time. But just to advertise it again, if you go and watch the follow-up talk, I go into a lot more detail about exactly what a view is, why these things are called views. And Chris finally says, are copies made during the transform? I'm concerned about performance with a very big vector compared to a for loop. So no, this no copies are made. Well, the way I have written it here, you're going to be copying one int, and then you're probably not even really going to be doing that. But this happens on the fly. We're not. This isn't transforming the whole vector and creating a new vector of all the transformed variables and then copying that into OStream. That's absolutely not what's happening here. That would be what happened if we had the eager algorithms. In this case, we've got the lazy algorithms, so this transformation is happening on the fly. So that's sort of the point of this. Okay, so completely unexpectedly, we are out of time. I was hoping that we that I might have a bit of time at the end, but just to very quickly finish off the slides, just because I promised at the beginning that I would mention this. How can we use this stuff today? Well, GCC version 10 comes with its complete support as far as I know. I haven't found anything that's missing. I have discovered one or two bugs, but each version of C++20, sorry, GCC, this gets better. MSVC, they started shipping ranges supporting 16.7. They're now up, I think it's 16.9, and according to their bug tracker on GitHub, at least, they are very, very close to complete ranges support. I think they've got all the algorithms. They've got all but 2 of the range adapters, as far as I know, last time I checked. If you're not using C++20 yet, if you're not using one of these brand new compilers, the very most famous implementation, the original implementation of all this stuff is called Range v3. You can see it at that, get it from there. Range v3 is the library from which all of this other stuff, all of this standardized stuff came. It's got an absolute ton of stuff, ton of extra views. It's also got things called actions that are not part of C++20. It's really popular. It's really widely used. I really recommend Range v3. Range v3 is great. In fact, the only thing, it's not really, but just because I have shown it off a couple of times, I have my own ranges implementation that I've done. So it doesn't use any Range v3 code. It's written from scratch from the published specifications. It's used to C++17. It doesn't use concepts. It uses this horrible Sweeney magic to emulate it. The nano part is because it aims to be small. It aims to just provide the C++20 features. And the idea is that if you're currently using C++17, nano range can be a stepping stone to standard ranges once you move to a C++20 conforming compiler. Right, so you can get all the benefits, you can get all the good stuff today by using nano range, and tomorrow, when your compilers have all updated, then you can move to namespace standard ranges. Hopefully, if I've done everything right, just by changing the namespace. So that is it. I would love actually to go on and answer more questions, but I think that we are out of time. So very many apologies to people whose questions I haven't managed to get to. Everyone was very quiet at the beginning, and I was a little bit worried that nobody was watching. But towards the end, we've now got lots of questions and not a lot of time. So very sorry about that. But I will be popping into Remo now. So if you want to come and have a chat with me, I will be very happy to talk to everybody. So thank you very much for your attention, and hope to see everybody in person at ACCU in 2022. Thank you very much.